Right now, beneath your feet, an iron ball the size of Pluto has stopped spinning the way it has spun for the last several 100 million years. That is not a metaphor. That is not a dramatization. That is the finding of a peer-reviewed study published in Nature Geoscience in January 2023 by researchers at Peking University who analysed decades of seismic wave data passing through the deepest interior of the planet and concluded that Earth's inner core has slowed its rotation relative to the mantle, paused, and may have begun rotating in the opposite direction. The inner core of the Earth, the dense, solid sphere of iron and nickel at the very centre of everything you have ever known. The object whose rotation generates the magnetic field that shields every living thing on the surface from lethal cosmic radiation. The engine that makes the compass point north, that deflects the solar wind, that holds together the invisible architecture of protection without which the atmosphere would be stripped away and every cell on the surface would be sterilized by charged particles from the sun within a generation. That engine has changed its rhythm, and no one can tell you with certainty what happens next. If you find that as unsettling as we do, stay with us. Like and subscribe, because what we are about to show you is not one anomaly. It is dozens, occurring simultaneously. Across every layer of the Earth system, from the inner core to the edge of the magnetosphere. Measured by instruments on 6 continents and in orbit. Published in journals. Confirmed by independent teams. And when you see them laid out together, in sequence, connected by the physics that links them, the picture that emerges is not a collection of curiosities. It is a portrait of a planet in the early stages of a transformation so fundamental that the last time it happened, it rewrote the rules of life on the surface. This is the story of what is happening to Earth right now. Not what might happen. Not what could happen. What is happening. Measured, confirmed, and almost entirely ignored by the public conversation. Let us begin. Start at the centre. The inner core is approximately 760 miles in radius. It is solid, despite temperatures exceeding 9,000 degrees Fahrenheit, because the pressure at that depth, more than 3.6 million atmospheres, forces iron into a crystalline state that no surface laboratory can replicate. The inner core is surrounded by the outer core, a 1,400-mile thick shell of liquid iron and nickel that flows in enormous convective currents, driven by heat escaping from the centre of the planet. Those currents are what generate Earth's magnetic field. The process is called the geodynamo. Liquid iron flows through an existing magnetic field. The motion of the electrically conductive fluid generates electrical currents. Those currents, in turn, produce magnetic fields that reinforce the original field. The system is self-sustaining as long as the flow continues. It has been operating for at least 3.5 billion years, producing the magnetosphere that makes the surface habitable. The inner core, sitting inside this ocean of liquid iron, does not spin at the same rate as the mantle and crust above it. It is mechanically decoupled from the rest of the planet by the liquid outer core. It can rotate slightly faster or slightly slower than the surface, and for decades the prevailing understanding was that it rotated slightly faster, a phenomenon called superrotation, at a rate of approximately 1 degree per year faster than the surface. Then, the seismic data from the Peking University study showed that the superrotation had stopped. The inner core's differential rotation had effectively paused around 2009, and the data was consistent with the core beginning to rotate slightly slower than the surface, a reversal of the previous trend. This is not the first time this has happened. The researchers found evidence in the seismic record that the inner core's rotation oscillates on a cycle of approximately 60 to 70 years. It speeds up, slows down, pauses, reverses, and then repeats. The last reversal appeared to have occurred in the early 1970s. The current pause and potential reversal aligns with the predicted timing of the next oscillation. If this was simply a geophysical curiosity, a rhythmic wobble deep inside the planet with no consequences at the surface, it would be interesting and nothing more. But the inner core's rotation is linked to the behavior of the magnetic field, to the length of the day, to the dynamics of the outer core flow, and, through those connections, to the behavior of the atmosphere, the oceans, and the biosphere. When the engine changes its rhythm, everything connected to the engine feels the change, and everything is connected to the engine. The magnetic field is the first and most direct connection, and the magnetic field is behaving in ways that have no precedent in the era of modern measurement. The total strength of Earth's magnetic field has decreased by approximately 9% over the last 200 years. That number, 9%, sounds modest, until you understand the baseline. The field has been decaying at an accelerating rate. The decline is not uniform. It is concentrated in specific regions, and, in one region in particular, the decay has reached a level that is causing real, measurable, operational consequences for the technology that civilization depends on. The South Atlantic Anomaly is a vast region stretching from South America to southern Africa, where the magnetic field is significantly weaker than the global average. Within this region, the field strength is approximately 30% below what models predict for that latitude. The anomaly has been growing. Over the last 2 decades, satellite data from the European Space Agency's SWARM mission shows that the South Atlantic Anomaly has expanded westward, deepened, and begun to split into 2 distinct lobes. Inside the South Atlantic Anomaly, the weakened magnetic field allows charged particles from the solar wind and cosmic rays to penetrate closer to the surface than they can anywhere else on Earth. The consequences are not theoretical, they are operational. Satellites passing through the anomaly experience increased rates of single-event upsets, random bit flips in their electronics caused by energetic particles striking their circuits. The Hubble Space Telescope, the International Space Station, and low Earth orbit communications satellites all take protective measures when passing through the region, powering down sensitive instruments or switching to redundant systems. Astronauts on the International Space Station report seeing flashes of light when they close their eyes while passing over the South Atlantic Anomaly. These flashes are Cherenkov radiation, produced when heavy ions from space penetrate the hull of the station and pass through the vitreous humor of the astronaut's eyes at speeds exceeding the speed of light in that medium. The astronauts are seeing cosmic rays with their retinas. Inside the supposedly protected environment of a spacecraft, inside the supposedly protected environment of the magnetosphere, the shield has a hole in it, and the hole is growing. But the South Atlantic Anomaly is a regional phenomenon. The global picture is in some ways more alarming. The North Magnetic Pole has moved. This is not unusual in itself. The magnetic poles drift. They have always drifted. But the rate and direction of the current drift are unprecedented in the era of measurement. For most of the 20th century, the North Magnetic Pole drifted slowly across the Canadian Arctic at approximately 10 kilometers per year. This was well within the range of expected behavior. The World Magnetic Model, maintained jointly by the United States and the United Kingdom for navigation purposes, was updated every 5 years, and the updates were routine. In the 1990s, the pole began to accelerate. By the 2010s, it was moving at approximately 55 kilometers per year, heading in a nearly straight line from the Canadian Arctic towards Siberia. The acceleration was so dramatic that the World Magnetic Model had to be updated ahead of schedule in 2019, an event that was described by the agencies involved as unusual but not alarming. 55 kilometers per year. The magnetic pole is not drifting, it is migrating. It is moving 5 times faster than it was a generation ago. And its trajectory has not curved or wavered. It is heading toward Russia in a straight line, as if drawn by something. The physical mechanism behind the pole's migration involves changes in the flow patterns of liquid iron in the outer core. Specifically, a region of intense magnetic flux beneath northern Canada has been weakening, while a competing region beneath Siberia has been strengthening. The pole is moving because the balance of power in the outer core has shifted. The rivers of molten iron, thousands of miles below the surface, have changed course. The connection between the core's behavior and the magnetic field's behavior is direct and causal. Changes in the inner core's rotation affect the dynamics of the outer core. Changes in the outer core change the magnetic field. Changes in the magnetic field change the magnetosphere. Changes in the magnetosphere change how much radiation reaches the upper atmosphere. Changes in upper atmospheric radiation change atmospheric chemistry. Changes in atmospheric chemistry change climate. The chain is long, but each link is established physics, and every link in the chain is currently showing anomalous behavior. Consider the atmosphere, not the weather, not the climate debate. The physical structure of the atmosphere itself. The mesosphere, the layer of the atmosphere between 50 and 85 kilometers altitude, has been cooling and contracting. This is a known consequence of rising carbon dioxide levels, which radiate heat more efficiently in the thin upper atmosphere than they trap it below. But the rate of contraction has exceeded model predictions by a factor of approximately 3. The mesosphere is shrinking faster than the physics of greenhouse gas forcing alone can explain. A contracting upper atmosphere changes the drag on objects in low Earth orbit. Satellites in orbits below 600 kilometers experience atmospheric drag that gradually lowers their altitude, requiring periodic reboosting to maintain their operational orbits. If the upper atmosphere shrinks, drag decreases, and satellites stay up longer. If the upper atmosphere expands during solar maximum, drag increases, and satellites come down faster. In February 2022, a geomagnetic storm caused by a coronal mass ejection from the Sun dumped energy into the upper atmosphere, causing it to expand temporarily. The expansion increased drag on 40 newly launched Starlink satellites, which had been deployed into a low initial orbit for checkout. The increased drag was sufficient to deorbit all 40 spacecraft before they could raise their orbits. They burned up in the atmosphere. The official explanation cited the geomagnetic storm, but the satellites were designed to survive moderate geomagnetic activity. The fact that a moderate storm destroyed an entire batch of spacecraft suggested that the baseline state of the upper atmosphere had already changed, that the starting condition was different from what the models predicted, and that the storm was the final push rather than the sole cause. The upper atmosphere is thinner than it should be, except when it is temporarily thicker than it should be. The variability has increased. The envelope of normal has expanded in both directions. And the instruments that depend on a stable upper atmosphere, which includes every satellite in low Earth orbit, are operating in an environment that no longer matches their design specifications. Below the mesosphere, in the troposphere and stratosphere where weather happens, the changes are even more visible. The jet streams, the high-altitude rivers of fast-moving air that circle the planet at the boundaries between warm and cold air masses, have begun to behave erratically. For decades, the northern hemisphere jet stream followed a relatively smooth, wave-like path from west to east. The waves, called Rossby waves, had predictable amplitudes and periods. Weather systems moved along the jet stream in orderly progression. Forecasting was difficult but tractable. In recent years, the jet stream has developed extreme meanders. Deep troughs plunge southward, dragging Arctic air to latitudes where it does not belong. Sharp ridges push northward, carrying tropical heat into the subarctic. The meanders have become more persistent, locking weather patterns in place for weeks at a time. This is the mechanism behind many of the most dramatic weather events of recent years. The heat dome over the Pacific Northwest in 2021, which killed hundreds of people and set temperature records by margins that climate models said were virtually impossible. The flooding in Pakistan in 2022, which submerged 1/3 of the country. The European heat waves that have become annual events. The standard explanation for the jet stream's increasing instability is the differential warming of the Arctic and the tropics. The Arctic is warming faster than any other region, reducing the temperature gradient that drives the jet stream. A weaker gradient means a weaker, wavier jet stream. This explanation is well supported by evidence and widely accepted. But there is an additional factor that receives less attention. The jet stream is an electromagnetic phenomenon as well as a thermodynamic one. The upper atmosphere is ionized. The jet stream flows through a medium that is electrically conductive. Changes in the magnetic field and in the flux of charged particles entering the upper atmosphere from space can influence the behavior of the jet stream through mechanisms that are poorly understood and rarely modeled. Some researchers have proposed that the weakening of the magnetic field, particularly the growth of the South Atlantic Anomaly, is allowing more energetic particles to reach the stratosphere over a larger area than before. These particles ionize air molecules, affecting cloud formation and atmospheric chemistry. The resulting changes in heating patterns could contribute to the jet stream's instability through a pathway that is entirely separate from greenhouse gas forcing. This is not a fringe idea. It is a published hypothesis that has appeared in peer-reviewed journals. It is also not a consensus view. The relationship between geomagnetic activity and weather is real, but its magnitude relative to other forcing factors is debated. What is not debated is that the magnetic field is weakening, that more particles are reaching the upper atmosphere, and that the atmosphere is behaving in ways that existing models do not fully capture. The Schumann resonances are electromagnetic resonances of the cavity formed between the surface of the Earth and the ionosphere. They are standing waves, like the resonant frequencies of a drum. The fundamental frequency is approximately 7.83 Hz, with harmonics at approximately 14.3, 20.8, 27.3, and 33.8 Hz. These frequencies have been remarkably stable for as long as they have been measured. They are determined by the size of the Earth ionosphere cavity and the speed of light, neither of which changes on human timescales. In recent years, monitoring stations have detected episodes of dramatically elevated Schumann resonance activity. The fundamental frequency has not changed, but the power of the resonances has spiked to levels far above the historical baseline. Bursts at frequencies of 30, 40, and even 80 Hz have been recorded. The interpretation of these bursts is disputed. Some researchers attribute them to increases in global lightning activity. Others suggest changes in the conductivity of the ionosphere, possibly related to increased particle flux from the weakened magnetic field. What is not disputed is that the electromagnetic environment at the surface of the Earth is changing. The frequencies that permeate the space in which you live, sleep, and think are not the same as they were 20 years ago. The implications of this for biology are uncertain but plausible. The human brain operates at frequencies that overlap with the Schumann resonances. Alpha waves, associated with relaxed wakefulness, oscillate at 8 to 12 Hz. Theta waves, associated with drowsiness and light sleep, oscillate at 4 to 8 Hz. There is a large body of research on the biological effects of low-frequency electromagnetic fields, and while the results are often contradictory and the mechanisms poorly understood, the idea that changes in the natural electromagnetic background could affect neurological function is not implausible. The subjective reports are widespread: increased anxiety, sleep disruption, a pervasive sense that time is moving faster. These reports are anecdotal and difficult to separate from the effects of modern life, social media, pandemic stress, and economic uncertainty. But they are remarkably consistent across cultures and geographies. And they coincide temporally with the measured changes in the Schumann resonance activity and the geomagnetic field. Correlation is not causation, but the correlation is there, and the physical mechanism is at least plausible. When the electromagnetic heartbeat of the planet changes, the organisms that evolved inside that heartbeat may notice. Now let us talk about something that should not be happening, but is. The Earth has been speeding up. The rotation of the Earth is slowing down over geological time. This is well-established physics. The gravitational interaction between the Earth and the Moon produces tidal friction that transfers angular momentum from the Earth's rotation to the Moon's orbit. The Earth slows down, the Moon moves farther away. The day gets longer by approximately 2.3 milliseconds per century. This is the long-term trend. It has been operating for billions of years. The day was approximately 6 hours long when the Moon first formed, 4.5 billion years ago. It has been getting longer ever since. The process is gradual, predictable, and inexorable. Except that in 2020, the Earth recorded 28 of the shortest days since precise atomic clock measurements began in the 1960s. The planet was spinning faster, not slower, faster. The length of day was decreasing by fractions of milliseconds, in direct contradiction to the long-term tidal trend. Milliseconds sound trivial. They are not. Global positioning systems, financial trading networks, communication satellites, and the entire architecture of precise timekeeping that modern civilization depends on are calibrated to the length of the day. The International Earth Rotation and Reference System Service, the body responsible for maintaining the official relationship between atomic time and astronomical time, was forced to consider the unprecedented step of implementing a negative leap second, subtracting a second from the clock rather than adding one. This had never been done in the history of timekeeping. Why did the Earth speed up? The standard explanation invokes the redistribution of mass. When ice sheets melt and the water flows into the oceans, the mass moves from high latitudes to lower latitudes. This should slow the Earth down, like a figure skater extending their arms. But the solid Earth also rebounds when the weight of ice is removed, and the resulting redistribution of mass within the mantle can have the opposite effect, speeding the rotation. The dynamics are complex, and the net effect depends on the specifics of where the ice is lost and how the mantle responds. Some geophysicists have proposed that the speed-up is related to changes in the coupling between the inner core and the mantle. If the inner core's rotation slowed down or paused, as the Peking University study suggests, angular momentum conservation requires that the mantle and crust speed up slightly to compensate. The total angular momentum of the Earth system must be conserved. If the core gives up angular momentum, the rest of the planet gains it. The speed up of the surface would be a direct consequence of the slowdown of the core. If this explanation is correct, the Earth's rotational speed-up is not a separate anomaly. It is a symptom of the same underlying cause as the magnetic field changes, the core dynamics. Everything is connected. The connections extend beyond the planet. When you look at the other bodies in the solar system, the anomalies are not confined to Earth. Mars. The InSight lander, which operated on the Martian surface from 2018 to 2022, detected seismic activity on a planet that was considered geologically dead. Marsquakes, some of them substantial. The largest, detected in May 2022, had a magnitude of approximately 5. On a planet with no active plate tectonics and no known volcanic activity, the source of these quakes remains unexplained. Some may be caused by the cooling and contraction of the planet's interior. Others may be caused by stresses from tidal forces or by processes in the Martian mantle that we do not yet understand. Jupiter. The planet's famous banded cloud structure has been changing. Entire bands of clouds have appeared and disappeared on timescales of months to years. The Great Red Spot, a storm that has been observed for at least 350 years, has been shrinking steadily. Its long axis has decreased from approximately 40,000 kilometers in the late 1800s to approximately 16,000 kilometers today. The shrinkage has accelerated in recent decades. No complete explanation has been offered for why a storm that persisted for centuries is now rapidly diminishing. Saturn, the planet's hexagonal polar vortex, a standing wave pattern at the North Pole that has been stable for decades, has shown signs of color changes and structural evolution that were not predicted. The ring system has also shown unexpected behavior, with material in certain ring gaps appearing and disappearing on short timescales. Uranus and Neptune. Both ice giants have shown anomalous brightening in recent observations. Neptune, which should be cooling as it moves farther from the Sun in its orbit, showed an unexpected warming trend in its stratosphere between 2018 and 2022. The warming was approximately 11 degrees Celsius over a few years, a change that no model predicted and no mechanism has been identified to explain. Pluto, the former 9th planet, now classified as a dwarf planet, showed atmospheric changes during the New Horizons flyby in 2015, and in subsequent stellar occultation measurements. Its atmosphere, which is produced by the sublimation of nitrogen ice on the surface, appeared to be collapsing, freezing back onto the surface faster than models predicted. Each of these observations, taken individually, has a plausible local explanation. Marsquakes from cooling contraction, Jupiter's bands from atmospheric dynamics, Neptune's warming from seasonal effects we do not fully model, Pluto's atmospheric collapse from orbital mechanics. But taken together, the pattern is striking. Multiple bodies in the solar system, at vastly different distances from the Sun, with vastly different compositions and internal structures, are all showing anomalous behavior simultaneously. The probability that all of these anomalies are independent, unrelated phenomena is not zero. But it invites the question of whether there is a common cause. One hypothesis is that the solar system is passing through a region of the interstellar medium with different properties than the region we have been travelling through for the last several million years. The heliosphere, the bubble of solar wind that surrounds the solar system, is shaped by the interaction between the solar wind and the interstellar medium. If the density or temperature or magnetic field strength of the interstellar medium changes, the heliosphere changes, and a changed heliosphere means a changed radiation environment for every planet inside it. The Voyager 1 and Voyager 2 spacecraft, which have crossed the boundary of the heliosphere and entered interstellar space, have detected conditions outside the bubble that were not fully predicted by models. The interstellar medium in our immediate neighbourhood appears to be somewhat denser and more magnetized than expected. The heliosphere itself has been found to be asymmetric, compressed on one side and stretched on the other, shaped by the pressure of the medium through which it moves. If the interstellar environment is changing, or if we are moving into a region with different properties, the effects would be felt throughout the solar system. More cosmic rays penetrating the heliosphere, more energetic particles reaching the inner planets, more energy being deposited in planetary atmospheres and possibly in planetary interiors through mechanisms involving the interaction of charged particles with magnetic fields and conductive materials. This is speculative. The data from Voyager is limited and the conclusions are preliminary. But the hypothesis is physically grounded, and it would explain why multiple planets are showing anomalous behavior at the same time. Back on Earth, the oceans are telling their own story of change. The Argo program, a global array of approximately 4,000 free-drifting profiling floats distributed across the world's oceans, provides continuous measurements of temperature and salinity from the surface to a depth of 2,000 meters. The data from Argo is unambiguous. Ocean heat content is rising at an accelerating rate. The oceans have absorbed approximately 90% of the excess heat trapped by greenhouse gases, and the total amount of energy stored in the oceans has increased dramatically in the last 2 decades. But the warming is not limited to the upper layers. Deep ocean measurements from the Argo program and from dedicated deep water surveys show that warming has penetrated to depths of 4,000 meters and below in some regions. The deep ocean, which was assumed to be insulated from surface changes on timescales of centuries to millennia, is warming on timescales of decades. This is significant for several reasons. The deep ocean is the thermal flywheel of the climate system. It absorbs heat slowly and releases it slowly. If the deep ocean is warming faster than expected, it means the climate system is absorbing more energy than models predict, or it means the heat is being transported downward more efficiently than models predict, or both. Either way, the models are wrong about something fundamental. The consequences for ocean circulation are particularly concerning. The Atlantic meridional overturning circulation, the system of currents that includes the Gulf Stream and that transports heat from the tropics to northern Europe, is driven by density differences between warm, salty surface water and cold, fresh, deep water. When surface water cools and becomes denser, it sinks, driving the circulation. Multiple studies have shown that the AMOC is weakening. The rate of weakening is debated, but the trend is consistent across different measurement techniques and different research groups. Some studies suggest the AMOC is weaker now than at any point in the last 1,000 years. Some models predict that the AMOC could collapse entirely within the next few decades, though this remains a minority view. If the AMOC weakens significantly or collapses, the heat distribution of the planet changes dramatically. Northern Europe loses its thermal subsidy from the tropics and cools. The tropics, no longer exporting heat northward, warm. Weather patterns shift. Agricultural zones move. The consequences for billions of people would be profound. And the AMOC is not the only circulation system showing signs of stress. The Southern Ocean circulation, which is critical for the global transport of heat and carbon, is also showing changes. Deep water formation around Antarctica appears to be slowing. The reasons are complex and involve both temperature and salinity changes, but the direction of change is the same. The Great Conveyor Belt of ocean circulation, which has operated in approximately its current configuration for millions of years, is showing signs of faltering. There is a deeper question here that connects the ocean changes to the core changes. The oceans are warming from above due to trapped heat from greenhouse gases. But there is also evidence that the oceans are warming from below. Geothermal heat flow from the ocean floor is typically a small contributor to ocean energy budgets, dwarfed by solar heating. But the ocean floor is not uniform. Mid-ocean ridges, volcanic seamounts, and hydrothermal vent systems release heat from the interior. If the interior is becoming more energetic, if the core and mantle are releasing more heat than they were a decade or two ago, the additional heat would enter the ocean from below. Measuring geothermal heat flow changes on a global scale is extraordinarily difficult. The ocean floor is vast, mostly unmapped, and largely inaccessible to direct measurement. The changes, if they exist, would be small relative to the total heat budget. But they would not need to be large to matter. The deep ocean is so cold that even a small increase in geothermal heat flux could have measurable effects on bottom water temperatures and circulation dynamics. Some researchers have noted anomalous warming in deep ocean basins that cannot be fully explained by surface-driven processes. The warming appears in regions far from major current systems, in basins that should be thermally isolated from surface changes on the timescales involved. If the warming is coming from below, it is yet another thread connecting the surface anomalies to the changes in the deep interior of the planet. The ocean is not the only fluid system on Earth showing signs of stress. The biosphere, the living layer of the planet, is responding to the changes in ways that are measurable, alarming, and in some cases, deeply strange. Marine mammals, particularly cetaceans, navigate using the Earth's magnetic field. Whales and dolphins have magnetite crystals in their brains, the same mineral that allows compass needles to point north. These crystals allow the animals to sense the direction and intensity of the magnetic field, and to use it for long-distance navigation across featureless ocean basins. Mass strandings of whales and dolphins have been recorded throughout history, but their frequency has increased in recent decades. The correlation between strandings and geomagnetic anomalies has been studied by multiple research groups. A 2017 study, published in the International Journal of Astrobiology, found a statistically significant correlation between solar storms and sperm whale strandings in the North Sea. The mechanism proposed was that solar-driven disturbances in the magnetic field created local anomalies that disoriented the whales, causing them to navigate into shallow waters. If the magnetic field is becoming more disturbed, more variable, more punctuated by sudden jerks and anomalies, the navigational problems for magnetically sensitive animals would increase. And indeed, strandings have been increasing. This is not merely a conservation concern, it is a signal. The animals that depend on the magnetic field for survival are telling us, through their behaviour, that the field is not working the way it used to. Birds are showing similar signs. Migratory species that have followed the same routes for thousands of generations are altering their paths. Some species are arriving at breeding grounds weeks earlier or later than historical norms. Others are failing to migrate entirely, remaining in northern latitudes through winters that were previously too harsh for survival. The disruption of migratory patterns is attributed primarily to climate change, and that attribution is well supported. But the magnetic field is also a factor. Many bird species use the magnetic field as one component of their navigational system, in combination with the sun, the stars, and learned landmarks. If the magnetic component becomes unreliable, the overall navigational accuracy degrades. Insects are affected too. Honeybees, whose waggle dance communicates the direction and distance of food sources relative to the sun, have been showing increasingly erratic dance patterns. Beekeepers in multiple countries have reported that colonies are becoming disoriented, with foraging bees failing to return to their hives at rates higher than historical norms. Colony collapse disorder, the phenomenon of entire hive populations disappearing, has been attributed to pesticides, parasites, habitat loss, and other factors. But the possibility that changes in the electromagnetic environment are contributing to bee disorientation has been raised by several research groups. The biosphere is a network of organisms that evolved inside a specific electromagnetic environment. That environment is changing, the organisms are responding, and the responses, from whale strandings to bee disorientation to bird migration disruption, all point in the same direction. The background conditions of life on Earth are not what they were. Let us go deeper into the geology, because the surface manifestations of the changes are visible, but the causes lie beneath. The number of significant earthquakes per year has not shown a clear upward trend in the instrumental record. This is important to state because the perception that earthquakes are increasing is widespread and often attributed to confirmation bias and improved detection. The global rate of magnitude 7 and above earthquakes has remained approximately constant at about 15 per year, but the distribution has changed. Earthquakes are occurring in places where they were previously rare. The central United States, historically one of the most seismically quiet regions on the continent, experienced a dramatic increase in seismicity beginning around 2009, with the annual number of magnitude 3 and above earthquakes increasing from a handful to over 1,000 by 2015. This was conclusively linked to wastewater injection from oil and gas operations, not to natural geological processes. It demonstrated that human activity can induce seismicity in regions that were previously stable. More relevant to our story are the volcanic developments. Volcanoes that have been dormant for thousands of years are showing signs of reactivation. The eruption of Fagradalsfjall in Iceland in 2021 occurred in a region that had not erupted in approximately 800 years. The subsequent eruptions in the same volcanic system in 2022 and 2023 suggest that a new period of volcanic activity has begun on the Reykjanes Peninsula, a region that has been quiet for centuries. The eruption of Cumbre Vieja on La Palma in the Canary Islands in 2021 was the first eruption on that island in 50 years. The eruption lasted 85 days and destroyed thousands of buildings. While 50 years is not an extraordinarily long dormancy, the eruption was notable for its intensity and duration. Globally, the number of eruptions per year has been relatively stable, though this is complicated by the fact that many submarine eruptions go undetected. What has changed is the seismic activity beneath some of the world's most dangerous volcanic systems. Campi Flegrei, the supervolcano that lies beneath the city of Naples, Italy, has been experiencing increasing uplift and seismic activity since 2005. The ground has risen by approximately 25 centimeters. The number and intensity of small earthquakes beneath the caldera have increased steadily. The system is not in imminent danger of eruption by most assessments, but the trend is clear and the direction is concerning. Yellowstone, the supervolcano beneath Wyoming, shows similar patterns of activity. Uplift, seismicity, and changes in the geothermal features at the surface, including the reactivation of Steamboat Geyser, which in 2018 began erupting more frequently than at any time in its recorded history. Yellowstone is monitored continuously, and the current assessment is that an eruption is not imminent. But the system is not dormant, it is dynamic, and it is changing. These volcanic changes are connected to the deeper planetary processes we have been discussing. Volcanic activity is driven by heat from the interior. If the interior is becoming more energetic, if the processes in the core and mantle are releasing more heat, that heat propagates upward through the mantle and eventually reaches the crust. The timescales are long, centuries to millennia, for deep mantle changes to manifest at the surface. But the currently observed increases in volcanic unrest at multiple systems worldwide are at least consistent with an increase in deep heat flux, even if the connection cannot be proven with current data. Beneath Antarctica, the situation is particularly intriguing. Subglacial volcanic activity has been detected under the West Antarctic ice sheet. Geothermal heat flow beneath the ice is higher than expected in several regions, contributing to the basal melting that is destabilizing the ice sheet from below. The discovery of mantle plumes, upwellings of hot material from deep in the mantle beneath Antarctica, has provided a mechanism for this enhanced heating. If the mantle plumes are becoming more active, the acceleration of Antarctic ice loss has a component that is entirely independent of atmospheric warming. This is not a small point. The stability of the Antarctic ice sheets is one of the most consequential variables in the climate system. The West Antarctic ice sheet alone contains enough ice to raise global sea level by approximately 3.3 meters if it were to collapse entirely. If the destabilization of this ice sheet has a component driven by internal planetary heat rather than solely by atmospheric warming, then our ability to predict and mitigate the consequences is reduced. We cannot control the heat coming from the mantle. We can only observe it and prepare for its effects. The permafrost regions of the Northern Hemisphere present a different but equally concerning picture. Permafrost, ground that remains frozen year-round, covers approximately 23 million square kilometers, roughly a quarter of the Northern Hemisphere's land surface. It has been stable for thousands of years. It is no longer stable. Permafrost temperatures have been rising across the Arctic. In some regions, the permafrost is actively thawing, releasing methane and carbon dioxide that have been locked in the frozen ground for millennia. Methane is a greenhouse gas approximately 80 times more potent than carbon dioxide over a 20-year time horizon. The amount of carbon stored in permafrost is estimated at approximately 1.5 trillion metric tons, roughly twice the amount currently in the atmosphere. The thawing of permafrost is a feedback loop. As the climate warms, permafrost thaws. As permafrost thaws, it releases greenhouse gases. As greenhouse gas concentrations rise, the climate warms further. As the climate warms further, more permafrost thaws. The loop is self-reinforcing, and once it crosses certain thresholds, it becomes self-sustaining regardless of what humans do with their emissions. But the permafrost holds more than carbon. Preserved in the frozen ground are microorganisms that have been dormant for tens of thousands of years. Viable bacteria have been revived from permafrost samples dating back hundreds of thousands of years. Viable viruses have been isolated from 30,000-year-old permafrost in Siberia. These organisms evolved in an environment that is radically different from the modern one. Their interactions with modern ecosystems and modern immune systems are entirely unknown. In 2016, an anthrax outbreak in Siberia was linked to the thawing of permafrost that exposed a reindeer carcass infected with anthrax spores. The carcass had been frozen for at least 75 years. The spores were still viable. A child died, and dozens of people were hospitalized. If organisms frozen for tens of thousands of years are also viable, the potential for encounters with pathogens against which modern humans have no immunity is real. The thawing permafrost is a box we are opening without knowing what is inside. The contents might be harmless. They might not. The Moon, Earth's only natural satellite, is involved in this story in ways that are both subtle and significant. The Moon is receding from the Earth at approximately 3.8 centimeters per year. This has been measured directly using laser retroreflectors left on the lunar surface by the Apollo missions. The recession is a consequence of the tidal interaction that is also slowing Earth's rotation. Angular momentum is transferred from the Earth's rotation to the Moon's orbit, causing the Moon to spiral outward. The current rate of recession is slightly faster than the long-term average derived from geological records. This discrepancy is small, and its significance is debated, but it is consistent with the broader picture of a system in which the distribution of angular momentum between the Earth and the Moon is not in a simple steady state, but is fluctuating on multiple timescales. The Moon's orbital dynamics have direct effects on the Earth through tides. The 18.6-year lunar nodal cycle, the period over which the plane of the Moon's orbit wobbles relative to the Earth's equatorial plane, modulates the height of tides. When the nodal cycle is in its amplifying phase, high tides are higher and low tides are lower. When it is in its suppressing phase, the opposite is true. The current nodal cycle is approaching its amplifying phase, which will peak in the mid-2030s. This means that coastal flooding events will become more frequent and more severe over the next decade, even without any further sea level rise. The combination of the nodal cycle amplification, ongoing sea level rise, and the land subsidence that affects many coastal cities creates a compounding effect that will push many coastlines past their infrastructure limits. This is not a prediction. It is a certainty based on orbital mechanics. The nodal cycle will amplify tides. Sea level is rising. Coastal infrastructure will be stressed. The only uncertainty is how much damage will result and how well communities will prepare. The gravitational field of the Earth itself is not constant. The GRACE and GRACE-FO satellite missions, which measure the gravitational field by precisely tracking the distance between two co-orbiting satellites, have revealed that the gravitational field changes on timescales of months to years. These changes are caused by the redistribution of mass, primarily water, across the surface and within the Earth. The GRACE data shows massive transfers of mass from ice sheets to oceans, from underground aquifers to the atmosphere and surface water systems, and from the solid Earth as it rebounds from the removal of ice loads. The gravitational field of the Earth is a real-time map of how mass is being redistributed across the planet, and that map is changing rapidly. Some of the changes detected by GRACE are not easily explained by surface processes alone. Gravitational anomalies in certain regions appear to be associated with changes in the density or distribution of material deep within the mantle. These deep signals are difficult to separate from the much larger surface signals, and their interpretation is uncertain. But they are consistent with the idea that the interior of the Earth is not static, that the redistribution of mass is occurring at all depths, and that some of the changes at the surface may be driven from below. Consider what all of this means when you step back and look at it as a single picture rather than a collection of separate phenomena. The inner core has changed its rotational behavior. The magnetic field is weakening and the poles are migrating at unprecedented rates. The South Atlantic Anomaly is growing. The upper atmosphere is contracting faster than models predict. The jet streams are becoming more unstable. The Schumann resonances are showing anomalous power bursts. The Earth's rotation briefly accelerated against its long-term trend. The oceans are warming at depth faster than expected. The AMOC is weakening. Volcanic systems that have been dormant for centuries are reactivating. The permafrost is thawing and releasing ancient carbon and ancient organisms. The gravitational field is showing changes that may have deep interior origins. And multiple other bodies in the solar system are showing anomalous behavior simultaneously. Each of these phenomena has been studied individually. Each has been published in reputable journals. Each has been attributed to a specific local cause: greenhouse gases, orbital mechanics, random variability, or unknown processes. And each attribution is reasonable when the phenomenon is considered in isolation. But the phenomena are not occurring in isolation. They are occurring simultaneously, on the same planet, connected by the same physical systems, driven by energy flows that originate in the same interior and the same external environment. The probability that they are all independent, that the timing is coincidental, that there is no common thread, is the probability that a very complicated system is experiencing a dozen unrelated perturbations at the same time purely by chance. That probability is not zero, but it is small enough to warrant the question of whether something more fundamental is occurring. The last time the magnetic field underwent a major reversal was approximately 780,000 years ago, the Brunhes-Matuyama reversal. The last time it underwent a significant excursion, a temporary but dramatic weakening and partial reversal, was approximately 41,000 years ago, the Lachance event. The Lachance event is the closest analogue in the geological record to what we may be witnessing the early stages of today. During the Lachance excursion, the magnetic field strength dropped to approximately 10% of its current value. The magnetic poles wandered erratically. The field structure became complex, with multiple magnetic poles appearing simultaneously at different latitudes. The excursion lasted approximately 1,000 to 2,000 years, with the period of maximum weakness lasting a few centuries. The consequences of the Lachance event for life on the surface are the subject of active research and significant debate. A 2021 study published in Science proposed that the weakened magnetic field during the Lachance event allowed a dramatic increase in cosmic radiation at the surface. The increased radiation, the study argued, contributed to the extinction of Neanderthals, forced early modern humans into caves, drove changes in vegetation across the Australian continent, and played a role in the megafaunal extinctions that occurred around the same time. This interpretation is controversial. Other researchers argue that the timing does not align precisely, that the climate changes of the period can be explained by other factors, and that the increase in surface radiation, while real, may not have been sufficient to cause the proposed effects. The debate is ongoing and unresolved. What is not debated is that the Lechauns event occurred, that the field weakened dramatically, that the weakening lasted centuries, and that it happened at a time of significant environmental and biological change. Whether the field weakening caused the changes or merely accompanied them is a question that the geological record cannot answer with certainty. The current rate of magnetic field decay, if it continues at its present rate, would reduce the field to Lechauns-like levels in approximately 1,500 to 2,000 years. That is a rough estimate based on linear extrapolation of a process that is not linear. The actual timeline could be longer or shorter. Some researchers have pointed out that the current rate of decay, combined with the accelerating pole migration and the growth of the South Atlantic Anomaly, is consistent with the early stages of an excursion or a full reversal. If a reversal or excursion is beginning, the process will not be instantaneous. It will unfold over centuries, but the effects will begin long before the reversal is complete. The weakening of the field, the growth of anomalous regions, the increase in radiation reaching the surface, the disruption of magnetically sensitive biological navigation, the increased vulnerability of electronic systems to solar storms, all of these will intensify gradually over decades and centuries. Modern civilization has never experienced a magnetic excursion. The last one occurred 41,000 years ago, when the most advanced technology on Earth was a stone tool. The infrastructure of the modern world, the electrical grids, the communications networks, the satellite constellations, the navigation systems, the power plants, the financial systems, is built on the assumption that the magnetic field will remain approximately as it is. That assumption may be wrong. A severe geomagnetic storm during a period of weakened magnetic field would have consequences that are difficult to fully model, but easy to describe in broad terms. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, caused telegraph systems worldwide to fail, some catching fire. A Carrington-class event today, with the field at its current strength, would cause widespread damage to electrical grids, satellite systems, and communications networks. A Carrington-class event during a period of Lachamp-level field weakness would be exponentially worse. The reduced shielding would allow far more energy to reach the surface. The induced currents in long conductors, power lines, pipelines, undersea cables would be far larger. The damage could extend to systems that are considered robust under current conditions. The Lloyd's of London insurance market, in a 2013 report, estimated that a Carrington-class event under current conditions could cause economic damage of between $0.6 and $2.6 trillion in the United States alone, with recovery times of 4 to 10 years for the most affected regions. Under conditions of a significantly weakened magnetic field, those estimates would need to be revised upward, possibly by an order of magnitude. This is not a reason for panic. The field is not going to collapse tomorrow. The process, if it is happening, will unfold over centuries. There is time to prepare, to harden infrastructure, to develop warning systems, to build resilience. But the time to start is now. And the first step is to acknowledge that the possibility is real. Let us end where we began, at the centre. 5,000 kilometres beneath your feet, an iron sphere the size of a small planet has changed its rotation. This change is connected through a chain of physical processes that are well understood in their individual links, but poorly understood in their collective behaviour, to the weakening of the magnetic field, the migration of the poles, the contraction of the upper atmosphere, the destabilization of the jet streams, the warming of the deep oceans, the reactivation of dormant volcanoes, the thawing of ancient permafrost, the disorientation of migratory animals, and the anomalous behavior of the Schumann resonances. The Earth is a system, a single, interconnected, dynamic system in which the core, the mantle, the crust, the oceans, the atmosphere, the magnetosphere, and the biosphere are linked by flows of energy and matter that operate on timescales from milliseconds to billions of years. When the system changes at its deepest level, the changes propagate outward. They reach the surface, they reach the sky, they reach the organisms that live between the rock and the stars. We are those organisms. We evolved inside this system. We are adapted to its current state. We depend on its current state for everything, from the air we breathe, to the magnetic field that protects us, to the climate that feeds us, to the gravitational stability that keeps our feet on the ground. The system is changing. The instruments confirm it. The data is published. The anomalies are accumulating. And the question that remains is not whether the changes are happening. The question is how deep they go, how fast they will proceed, and whether the comfortable stability that we have treated as a permanent feature of our home is, in fact, a temporary condition that the planet is in the process of leaving behind. The Earth does not owe us stability. It has been stable, mostly, for the few thousand years of recorded civilization. That stability is what allowed agriculture, cities, technology, science, everything we are and everything we have built. But the geological record shows that stability is the exception, not the rule. The Earth's history is a history of change, of phase transitions, of catastrophic reorganizations, interspersed with long periods of relative calm. We may be at the end of a calm period. We may be at the beginning of a transition. We do not know with certainty. The instruments are not yet precise enough, and the time series are not yet long enough to distinguish between a temporary fluctuation and the onset of a fundamental change. But the instruments are screaming. They are screaming in the language of data, in the language of graphs and tables and peer-reviewed papers. They are screaming that the inner core has changed its rotation, that the magnetic field is weakening, that the poles are racing across the Arctic, that the atmosphere is contracting, that the oceans are warming from below, that the permafrost is opening ancient vaults, that the other planets are changing too. The Earth is speaking. In the language of seismic waves and magnetic field lines and ocean temperatures and atmospheric chemistry. It is speaking louder than it has spoken at any time in the era of human measurement. The question is whether we are listening. The data says we should be. The instruments are still recording. The anomalies are still accumulating. And somewhere, 5,000 kilometers below your feet, an iron ball the size of a small planet is turning in a new direction. It does not know you are here. It does not care that you are here. It is simply doing what the physics requires. And the physics right now requires something different from what it required a decade ago. That is the story. Not of one anomaly, but of many. Not of one system, but of all systems. Not of one planet, but of a planet and its star and its solar system and the patch of galaxy through which it is currently travelling at 828,000 kilometers per hour. Something is happening to Earth. The instruments know it. The animals know it. The oceans know it. The ice knows it. The volcanoes know it. Now you know it too. What you do with that knowledge is up to you. But the planet is not waiting for your decision. It is already moving. It has already changed. And the next change is already building, deep in the iron heart of the world, where no light has ever reached, and no human hand will ever touch. The Earth is not the stable, predictable, reliable platform you were taught it was. It is a dynamic, evolving, self-organizing system that is currently undergoing a shift in its deepest operating parameters. The shift is real. The evidence is measured. The consequences are beginning. And we are standing on top of all of it, looking up at a sky that is beginning to glow in new colors, listening to sounds that have no explanation, feeling, in some deep biological register that we cannot name, that the ground beneath us is not quite what it was. Trust that feeling. The instruments agree with it. But we are not finished, because the story extends far beyond seismology and magnetism. It reaches into the chemistry of the air you breathe, the behavior of the water that covers 71% of the surface, the biology of every organism that navigates by magnetism, and the fragile infrastructure on which 8 billion human lives depend. Each of these domains is showing its own anomalies. Each anomaly, when examined carefully, traces back to the same set of deep causes. And when you see them together, the picture is not ambiguous. It is coherent. It is alarming. And it is far larger than any single discipline has acknowledged. Start with gravity. Gravity is supposed to be the most constant of all physical forces. The gravitational constant, g, is one of the fundamental parameters of the universe. It does not change. It does not fluctuate. It is the same everywhere and at all times. That is the assumption. That is what every physics textbook states. Except that when different laboratories around the world measure g with their most precise instruments, they get different answers. Not wildly different, but different enough that the discrepancy exceeds the stated experimental uncertainties. The CODATA recommended value of g has an uncertainty of approximately 1 part in 10,000, which is remarkably poor for a fundamental constant. The speed of light is known to 1 part in a billion. The charge of the electron is known to parts per trillion. But g, the constant that describes the force holding you to the planet, is known only to 1 part in 10,000. This imprecision is itself an anomaly. It suggests that either our measurement techniques for gravity are fundamentally limited in ways that our techniques for electromagnetism are not, or that g is not perfectly constant, that it varies slightly depending on when and where you measure it. A series of experiments over the past 2 decades have reported small but systematic variations in the measured value of g that correlate with time. Some researchers have claimed to detect a periodic oscillation in g with a period of approximately 5.9 years, which would correlate with certain solar cycles. Others have found no such oscillation. The debate is unresolved. The measurements are at the edge of instrumental sensitivity, and systematic errors are difficult to rule out. But if g does vary, even at the parts per million level, the consequences for our understanding of the Earth system are profound. The internal dynamics of the Earth, the convection in the mantle, the behavior of the core, the propagation of seismic waves, all depend on gravity. A small change in g would change the equilibrium conditions inside the planet. It would change the forces acting on the liquid outer core. It would change the dynamics of the geodynamo. It could, in principle, trigger exactly the kind of core behavior changes that we are observing. This is speculative. The evidence for variations in G is not conclusive. But the measurements are there, published, debated, and not resolved. And the possibility that the most fundamental force in the universe is not as constant as we assume deserves to be on the table when we are trying to understand why the planet is behaving in unprecedented ways. The GRACE satellites have given us another window into gravitational anomalies. Their measurements of Earth's gravitational field reveal a world that is far from the smooth, uniform sphere that we imagine. The gravitational field of the Earth is lumpy. There are regions where gravity is measurably stronger and regions where it is measurably weaker. The differences are small, but they are real, and they are mapped with extraordinary precision. One of the most striking features of Earth's gravitational field is a massive low point in the Indian Ocean. The sea surface in this region is approximately 106 meters lower than the global average. Not because the water has been scooped out, but because the gravitational pull is weaker there. Less gravity means the ocean surface is pulled down less, creating a gravitational valley in the sea. The cause of this anomaly has been debated for decades. Recent research published in 2023 suggests that it is the remnant of an ancient tectonic event, the subduction of the Tethys seafloor deep into the mantle over the past 100 million years. Dense slabs of ancient ocean floor sinking through the mantle created density anomalies that persist to this day. The gravitational low in the Indian Ocean is a scar from a collision that happened before the dinosaurs went extinct. And this scar appears to be changing. Gravity measurements show that the anomaly is not static, it shifts, it pulsates. The material deep in the mantle that creates the anomaly is in motion, slowly but measurably, carried by convective flows that operate on timescales of millions of years, but that produce detectable changes over decades. These deep gravitational changes interact with the surface in ways that are still being mapped. Changes in the gravitational field affect ocean circulation. They affect the distribution of water mass. They affect the stress patterns in the Earth's crust. A shifting gravitational anomaly is a shifting foundation, and everything built on that foundation shifts with it. Now consider the infrastructure. Modern civilization is an electrical organism. It runs on current. It communicates through electromagnetic signals. It navigates by satellites that depend on precise timing and precise positioning, both of which depend on a stable electromagnetic environment. The power grid is the most vulnerable system. Long-distance transmission lines, the backbone of electrical distribution, are essentially antennas hundreds of kilometers long. When the magnetic field fluctuates rapidly, as it does during geomagnetic storms, it induces currents in these long conductors. These geomagnetically induced currents flow through the power grid, saturating transformers, causing them to overheat, and in the worst case, permanently damaging them. High-voltage transformers are the critical nodes of the power grid. They are custom-built. They are expensive, and they take months to years to manufacture and install. There is no strategic reserve of spare transformers sufficient to replace even a fraction of those that would be damaged in a severe geomagnetic storm. If a Carrington-class event occurred today, estimates suggest that between 300 and 350 high-voltage transformers in the United States alone could be damaged or destroyed. Replacing them would take years. During those years, regions served by those transformers would be without reliable electricity. Without electricity, water treatment plants stop operating, fuel pumps stop working, refrigeration fails, communication networks go dark, financial systems collapse. The cascade of failures from the loss of the electrical grid propagates through every system that depends on it, which in the modern world is every system. This vulnerability is not new. It has been recognized and studied for decades. Reports have been written, recommendations have been made, and very little has been done. The cost of hardening the grid against geomagnetic storms is estimated at tens of billions of dollars. That is a large number. It is also approximately 1% of the economic damage that a severe storm would cause. The cost-benefit analysis overwhelmingly preparation. But preparation requires action, and action requires political will, and political will requires public awareness of the threat. The threat is growing. The magnetic field is weakening. The South Atlantic Anomaly is expanding. The protection against geomagnetically induced currents is declining in precisely the period when solar activity is increasing. Solar Cycle 25, which began in December 2019, has been more active than forecast. The number of sunspots and the frequency of large flares have exceeded predictions consistently. The peak of the cycle is expected between 2025 and 2026, and the activity level at that peak may be significantly higher than the moderate peak that was originally forecast. The combination of increasing solar activity and decreasing magnetic protection is a convergence that has not occurred in the era of electrical infrastructure. Every previous solar maximum in the age of the power grid occurred with a stronger magnetic field than the current one. We are entering uncharted territory. Not in the sense that the physics is unknown, the physics is well understood, but in the sense that the specific conditions, strong solar activity plus weak magnetic field, have not been tested against modern infrastructure. The test is coming. The question is whether the infrastructure will pass. Undersea cables carry approximately 97% of intercontinental data traffic. These cables, typically about the diameter of a garden hose, lie on the ocean floor, spanning thousands of kilometers between continents. They are the physical backbone of the global internet. Without them, international communication would be reduced to satellite links with a tiny fraction of the bandwidth. Undersea cables are vulnerable to geomagnetically induced currents for the same reason that power lines are. They are long conductors in a changing magnetic field. The repeaters that amplify signals along the cable every 50 to 100 kilometers are powered by electrical current sent through the cable from shore stations. Geomagnetically induced currents can disrupt this power supply, causing repeater failures and signal loss. A 2021 study by researchers at the University of California, Irvine, modeled the effects of a Carrington-class geomagnetic storm on the undersea cable network. The study found that the most vulnerable links were the long-distance cables crossing the Atlantic and Pacific, precisely the links that carry the most traffic. A severe storm could cause widespread outages lasting weeks to months. The study described the scenario as an internet apocalypse, a phrase that was widely reported and just as widely forgotten. The vulnerability of undersea cables is compounded by the geological changes we discussed earlier. New fractures and fissures on the ocean floor, increased seismic activity in previously quiet regions, submarine landslides triggered by warming ocean temperatures, and destabilized methane hydrates. All of these increase the physical risk to cables that were laid in locations chosen for their geological stability. If the geological stability is no longer guaranteed, the cable routes may need to be reassessed. But the cost and complexity of relaying transoceanic cables are enormous, and the decisions about cable routing are made by private companies whose planning horizons are measured in decades, not centuries. The interaction between the changing electromagnetic environment and the human body is a subject that mainstream science approaches with caution for good reason. The history of claims about electromagnetic fields and health is littered with poorly designed studies, sensationalized media reports, and outright pseudoscience. The caution is warranted, but the caution should not extend to ignoring real evidence. And the evidence that geomagnetic activity affects human biology is substantial. Multiple studies have found correlations between geomagnetic storms and cardiovascular events. A 2014 meta-analysis published in the International Journal of Biometeorology reviewed 22 studies and found a statistically significant association between geomagnetic activity and the incidence of myocardial infarction. A 2018 study in the journal Scientific Reports found that hospital admissions for stroke increased during periods of high geomagnetic activity. The mechanisms proposed include effects on blood viscosity, heart rate variability, and autonomic nervous system function. The human body contains magnetite crystals, primarily in the brain, specifically in the meninges, and in association with the hippocampus and cerebellum. These crystals are biogenic, produced by the body itself through a process that is not fully understood. Their function, if any, is debated, but their presence suggests that the human brain has the physical hardware to detect magnetic fields, even if we are not consciously aware of the detection. Research published in 2019 by Caltech neuroscientist Joseph Kirschvink demonstrated that human brainwaves respond to controlled changes in the ambient magnetic field. Using a Faraday cage to shield participants from external electromagnetic noise, Kirschvink showed that rotating a magnetic field of Earth strength around a participant's head produced measurable changes in alpha wave power, the same frequency band that overlaps with the Schumann resonance. The response was not conscious. Participants did not report feeling anything, but the EEG data showed a clear, repeatable signal. This means the human brain responds to changes in the magnetic field even though we are not aware of the response. If the ambient magnetic field is becoming more variable, more subject to jerks and bursts and anomalies, the brain is registering those changes below the threshold of consciousness. The effects might manifest as changes in mood, sleep quality, cognitive function, or stress response. They would be subtle. They would be difficult to distinguish from the 1,000 other factors that affect these outcomes. They would be easy to dismiss, and they would be real. The reported increase in anxiety, insomnia, cognitive fog, and the subjective sense that time is accelerating may or may not be caused by geomagnetic changes. The evidence is suggestive, but not conclusive. What is conclusive is that the magnetic environment is changing, that the human brain responds to the magnetic environment, and that the changes in the magnetic environment are in the same direction, more variable, more energetic, more unpredictable as the reported changes in human well-being. The connection is plausible. The dismissal of the connection is premature, and the investigation of the connection is woefully underfunded relative to its potential significance. Now consider the deep biosphere. The discovery that life extends deep into the Earth's crust, far below the regions reached by sunlight or surface processes, is one of the most remarkable findings in modern biology. Drilling operations and mine explorations have found living microorganisms at depths of more than 5 kilometers. The total biomass of the deep biosphere is estimated to contain between 15 and 23 billion metric tons of carbon, representing a significant fraction of all life on Earth. These deep organisms are extremophiles. They survive in conditions of extreme pressure, extreme temperature, and extreme isolation. They metabolize rock. They use chemical energy from reactions between water and minerals to power their biology. They live in a world without sunlight, without oxygen, without any of the things that surface life considers essential. The deep biosphere operates on geological timescales. Its metabolic rates are extraordinarily slow. A single generation of deep microorganisms may take decades or centuries. Their world changes on timescales measured in millions of years. Or it used to. Recent studies have detected changes in deep biosphere activity that correlate with changes in the geothermal environment. As the Earth's interior becomes more energetically active, as heat flow from the core and mantle increases, the temperature and chemistry of the deep environments change. Microorganisms that have been metabolizing at near zero rates for millions of years are encountering warmer, more chemically rich conditions. Some of them are responding by increasing their metabolic activity. They are producing more gases. They are changing the chemistry of groundwater. They are, in a very real sense, waking up. The consequences of a waking deep biosphere are poorly understood. The gases produced by deep microorganisms, including methane, hydrogen sulfide, and carbon dioxide, can percolate upward through fractures and porous rock. They can enter groundwater systems, aquifers, and eventually the atmosphere. The quantities involved are uncertain, but potentially significant. If the deep biosphere begins outgassing at rates significantly above its historical baseline, the effect on atmospheric chemistry could be measurable. There is also the question of what happens when deep organisms reach the surface. Thermophilic bacteria from deep environments have been found in hot springs and volcanic vents, where they interact with surface ecosystems. But if new fractures and fissures are opening in the crust, as the geological evidence suggests, new pathways for deep organisms to reach the surface are being created. The mixing of deep biosphere organisms with surface ecosystems is an uncontrolled experiment with unknown consequences. Cosmic dust is another factor that connects the changes on Earth to the changes in the broader solar system. The Earth accumulates approximately 40,000 to 60,000 metric tons of cosmic dust per year, material that drifts in from interplanetary space and settles through the atmosphere. Most of this material is microscopic, particles smaller than a grain of sand, and it reaches the surface without incident. But the composition and quantity of cosmic dust vary depending on where the solar system is in its orbit through the galaxy and what local features it encounters. The solar system is currently embedded in what astronomers call the local interstellar cloud, a warm, diffuse cloud of gas and dust approximately 30 light-years across. We entered this cloud sometime in the last few thousand to few 100,000 years, and we will exit it in approximately 10,000 to 20,000 years. The local interstellar cloud is not uniform. It has denser and thinner regions. As the solar system moves through these regions, the flux of interstellar dust entering the heliosphere and reaching the inner planets changes. Some researchers have proposed that the current period of planetary anomalies could be related to the solar system encountering a denser region within the cloud. Interstellar dust particles are different from interplanetary dust. They carry information about the chemical composition of the interstellar medium. They may contain complex organic molecules, water ice, and silicate minerals with compositions distinct from local solar system material. When these particles enter the atmosphere, they can serve as condensation nuclei for cloud formation, alter the chemistry of the upper atmosphere, and introduce exotic materials into the biosphere. Noctilucent clouds, the eerie blue-white clouds that appear in the mesosphere at heights of approximately 80 kilometers, are formed when water vapor condenses onto dust particles at extremely low temperatures. These clouds have been appearing more frequently and at lower latitudes than historically observed. Their increased frequency is attributed to rising methane concentrations, which produce water vapor when oxidized in the upper atmosphere. But the availability of condensation nuclei, which may be linked to the influx of cosmic and interstellar dust, is also a factor. The sky is literally different from what it was. The dust in the upper atmosphere is different. The clouds are different. The chemistry is different. And all of these changes are connected to the solar system's passage through a medium that we cannot control and can barely observe. The phenomenon of skyquakes, mysterious booming sounds from clear skies, has been reported with increasing frequency across the world. These sounds, variously described as resembling cannon fire, explosions, or thunder from a cloudless sky, have been documented in coastal and inland regions across every continent. They have been reported for centuries, but the frequency of reports has increased dramatically in the last decade. Multiple hypotheses have been proposed. Meteors entering the atmosphere at steep angles and detonating at high altitude would produce a sound reaching the ground without a visible fireball. Military aircraft breaking the sound barrier at high altitude would produce sonic booms. Earthquake-related gas releases from the sea floor or from underground could produce explosive sounds. None of these hypotheses fully explains the pattern of observations. Skyquakes occur in regions far from military flight paths. They occur when meteor activity is low. They occur in places with no seismic activity. The sounds are often described as coming from directly overhead, which is inconsistent with many of the proposed mechanisms. Some researchers have proposed that skyquakes are related to electrical discharge events in the upper atmosphere, phenomena related to the sprites, blue jets, and other transient luminous events that have been documented above thunderstorms. These discharges involve enormous energy transfers between the atmosphere and the ionosphere. If the electrical potential between the surface and the ionosphere is increasing, as several lines of evidence suggest, the frequency and intensity of these discharge events would also increase. The associated shock waves could produce the sounds reported as skyquakes. The electrical circuit of the Earth, the current that flows continuously between the surface and the ionosphere, maintained by thunderstorm activity worldwide, is showing signs of intensification. Lightning activity has been detected in the Arctic, where it was previously extremely rare. The intensity of individual lightning strikes has been increasing. Mega flashes, single lightning bolts that extend hundreds of kilometers horizontally through cloud layers, have been documented with increasing frequency, with the current record standing at 768 kilometers, spanning from Texas to Mississippi. The atmosphere is electrically more active than it has been in the period of modern measurement. This increased activity is consistent with the changes in the magnetosphere, which modulates how much solar and cosmic energy reaches the upper atmosphere. It is consistent with the changes in the ionosphere, which is being bombarded by more energetic particles as the magnetic shield weakens. And it is consistent with the changes in the atmospheric chemistry, which affects conductivity and charge separation. The Earth's electrical system is being overcharged, and the discharges, the lightning, the sprites, the skyquakes, are the visible and audible symptoms of an electromagnetic environment that is out of its normal operating range. The changes are not limited to the physical environment. They extend into the biological environment in ways that are measurable and, in some cases, deeply unsettling. The nutritional content of food crops has been declining for decades. Multiple studies have documented decreases in the concentrations of protein, iron, zinc, and other nutrients in wheat, rice, corn, and other staple crops. The primary driver identified in the literature is the increase in atmospheric carbon dioxide, which stimulates plant growth but dilutes the nutrient content of the resulting biomass. Plants grow bigger but contain less nutrition per unit weight. But there may be an additional factor. Plant roots absorb nutrients from the soil through electrochemical processes that are influenced by the ambient electromagnetic environment. The rate of ion exchange, the efficiency of nutrient uptake, the signaling between mycorrhizal fungi and root cells all involve electrical and magnetic phenomena at the molecular level. If the ambient electromagnetic environment is changing, these processes could be affected. This is not well studied. The interaction between geomagnetic field changes and plant nutrition is a topic that sits at the intersection of geophysics and agricultural science, two fields that rarely communicate. But the possibility is worth considering. If the declining nutritional content of crops has a geophysical component, it would not be addressed by any of the agricultural interventions currently being pursued. It would be a problem with no solution except adaptation, because we cannot control the magnetic field. The forests of the world are showing signs of stress that go beyond the well-documented effects of climate change, drought, and insect infestation. In temperate and boreal forests across the northern hemisphere, trees are growing faster but dying younger. This paradox, documented in multiple long-term forest monitoring studies, suggests that the trees are responding to an increase in available energy, growing rapidly, but at the cost of structural integrity and lifespan. The wood they produce is less dense, less strong, and more vulnerable to wind damage and disease. The phenomenon of drunken forests, stands of trees tilting at odd angles like sailors on a ship deck, has long been associated with the thawing of permafrost, which destabilizes the ground. But drunken forests have been observed in regions far from permafrost, in temperate zones where the ground should be stable. The implication is that the ground is not stable. Micro-movements of the crust, settling, shifting, responding to changes in groundwater levels and deep stress patterns, are affecting the root hold of trees across wide areas. The mycorrhizal networks that connect trees underground, sometimes called the wood wide web, are also showing changes. These networks, formed by fungal filaments that link the root systems of trees over hundreds of meters, allow trees to share nutrients, water, and chemical signals. Research has shown that the health and connectivity of these networks are declining in many forest ecosystems. If the networks are disrupted, the trees they connect become more isolated, more vulnerable, and less able to respond collectively to stress. The forest is not just a collection of trees, it is a network, an electrical and chemical communication system that is embedded in the ground, in the water table, in the electromagnetic field of the planet. When the background conditions change, the network changes, and when the network degrades, the forest degrades with it. The ocean is showing its own set of biological anomalies. Phytoplankton, the microscopic organisms that produce approximately half of the world's oxygen through photosynthesis, are declining in abundance. A 2010 study published in Nature estimated that global phytoplankton populations had declined by approximately 40% since 1950. The causes cited included rising ocean temperatures, increased stratification reducing nutrient mixing, and changes in ocean chemistry. But phytoplankton are also sensitive to light, specifically to the spectrum and intensity of light that penetrates the ocean surface. If the spectral characteristics of sunlight reaching the surface are changing, as they would if the atmospheric composition and the ozone layer are changing, the conditions for phytoplankton photosynthesis change. Some species would benefit from the shift, others would be disadvantaged. The community composition would change, with cascading effects through the marine food web. The oxygen we breathe is produced by photosynthesis, both on land and in the ocean. If the ocean's photosynthetic capacity is declining, the global oxygen budget is affected. The effect is currently small, unmeasurable against the vast reservoir of atmospheric oxygen. But the trend is in the wrong direction. And if the trend accelerates, driven by changes in ocean temperature, chemistry, circulation, and light environment, the consequences over decades to centuries could be significant. There is a phenomenon observed in the deep ocean that connects to the seismic and gravitational changes we discussed. The rogue wave. A wave of extraordinary height that appears without warning in otherwise moderate sea conditions, has been documented with increasing frequency. These waves, which can reach 30 meters or more, were once dismissed as sailors' tales. They are now established fact, detected by offshore platforms, research vessels, and satellites. The causes of rogue waves are complex and involve the interaction of wave trains, currents, and wind patterns. But some researchers have proposed that subtle changes in ocean floor topography caused by seismic activity, submarine landslides, or the shifting of sediment layers could alter the patterns of wave propagation in ways that increase the frequency of rogue wave formation. If the ocean floor is more active than it used to be, if new fractures and shifts are occurring at rates above the historical baseline, the conditions for rogue wave formation would be enhanced. The economic implications are significant. Maritime shipping carries approximately 90% of global trade. Ships are designed to survive specified sea states. If the frequency and intensity of extreme wave events increase beyond the design parameters, the risk to shipping increases, insurance costs rise, and the reliability of global supply chains decreases. This is not a hypothetical concern. The insurance industry has noted an increase in losses from extreme ocean conditions in recent years. Return for a moment to the subject of ancient civilizations and their possible awareness of the cycles we are discussing. Göbekli Tepe, the archaeological site in southeastern Turkey, was constructed approximately 11,600 years ago, at the very end of the Younger Dryas, a period of abrupt and severe climate change that followed the end of the last ice age. The site consists of massive stone pillars carved with animal reliefs and arranged in circular enclosures. The construction required coordinated labour on a scale that was not supposed to exist in that era. The site predates agriculture, pottery, and settled communities. One interpretation of Göbekli Tepe, proposed by researchers including Graham Hancock, is that it was deliberately constructed to record astronomical observations and to encode information about cyclical catastrophes. The carvings on the pillars have been interpreted as representing specific constellations in specific positions, potentially encoding the date of a catastrophic event. A 2017 paper, published in Mediterranean Archaeology and Archaeometry, analysed the carvings on a particular pillar, known as the Vulture Stone, and proposed that it recorded a comet impact at approximately 10,850 BCE, coinciding with the onset of the Younger Dryas. This interpretation is disputed. Mainstream archaeology generally does not accept that Göbekli Tepe was an observatory, or that its carvings encode specific astronomical dates. The methodological challenges of interpreting symbolic art as astronomical data are significant, but the timing is striking. Göbekli Tepe was constructed at the end of a catastrophic climate event. The Younger Dryas saw average global temperatures drop by approximately 5 to 7 degrees Celsius in a matter of decades, an event so sudden that it has been attributed by some researchers to an extraterrestrial impact or airburst. The evidence for the Younger Dryas impact hypothesis includes a widespread layer of nanodiamonds, magnetic spherules, and soot dated to approximately 12,800 years ago. If the Younger Dryas was caused or triggered by an external event, the coincidence of catastrophic climate change, possible astronomical impact, and the construction of a monumental site that may encode astronomical information becomes more interesting. It suggests that the humans who survived the catastrophe were motivated to preserve knowledge about its cause, possibly as a warning to future generations. Whether this interpretation is correct is a question for future research, but the pattern of catastrophic climate events at intervals of approximately 12,000 years, coinciding with the precession of the equinoxes, has been noted by multiple researchers. If such a cycle exists, and if we are currently at a point in that cycle where the probability of catastrophic change is elevated, then the current anomalies we are observing, the magnetic field changes, the core dynamics, the atmospheric and oceanic disruptions, might be the early manifestations of a cyclical phenomenon that our ancestors experienced and tried to warn us about. The precession of the equinoxes is a slow wobble in the Earth's rotational axis, with a period of approximately 25,772 years. It is caused by the gravitational pull of the Sun and the Moon on the Earth's equatorial bulge. The wobble changes the orientation of the Earth's axis relative to the stars, causing the pole star to change over time and the apparent positions of the equinoxes against the background of the zodiac to shift. Precession does not, by itself, cause climate change or geological upheaval, but it modulates the seasonal distribution of solar radiation, which affects the growth and retreat of ice sheets. And it changes the Earth's orientation relative to the galactic plane, which some researchers have suggested could affect the flux of cosmic rays reaching the solar system. The idea of a galactic connection to terrestrial climate is speculative, but not without support. The solar system oscillates above and below the galactic plane as it orbits the galactic center. The period of this oscillation is approximately 60 to 70 million years. When the solar system is above or below the plane, it is more exposed to cosmic rays from extragalactic sources. When it crosses the plane, the local density of gas and dust may affect the heliosphere. Some researchers have found correlations between the timing of galactic plane crossings and mass extinction events, though these correlations are debated. On shorter timescales, the solar system's passage through the spiral arms of the galaxy, which occurs every few 100 million years, also changes the cosmic ray environment. And the local conditions within the current spiral arm, the density and magnetization of the interstellar medium, the proximity to recent supernovae, the structure of the local bubble of hot gas in which the solar system is embedded, all affect the shielding that the heliosphere provides. We are not isolated from the galaxy, we are embedded in it, we move through it, and the conditions we encounter as we move change the environment at every scale, from the boundary of the heliosphere to the surface of the Earth to the depths of the core. The convergence of changes on Earth, in the solar system, and potentially at the galactic scale, suggests that we may be experiencing a period of heightened variability that is driven by factors at multiple scales simultaneously. Internal factors, the dynamics of the core and mantle. Solar factors, the increasing activity of the current solar cycle. Interstellar factors, the properties of the medium we are passing through. Galactic factors, our position within the spiral arm and relative to the galactic plane. Each factor alone might produce small, manageable changes. Together, they may produce changes that are larger than the sum of their individual contributions, because the Earth system is non-linear. Small perturbations can trigger large responses when the system is near a tipping point. And the evidence suggests that multiple Earth systems, the magnetic field, the ocean circulation, the ice sheets, the permafrost, are currently near their respective tipping points. The concept of a cascade of tipping points, where the crossing of one threshold triggers the crossing of another, which triggers the crossing of another, is one of the most concerning ideas in Earth system science. If the AMOC collapses, it changes the heat distribution of the planet, which accelerates ice sheet loss, which changes the gravitational field and ocean circulation further, which affects permafrost thawing, which releases more greenhouse gases, which accelerates warming, which weakens the AMOC further. The loop is self-reinforcing. Once it begins, it is extraordinarily difficult to stop. The question of whether we are approaching such a cascade, or whether we are already in the early stages of one, is one of the most important questions in science. The answer will be determined not by theory, but by observation. And the observations, as we have documented throughout this video, are pointing in a consistent direction. Every major Earth system is showing anomalous behavior. The anomalies are interconnected, and the rate of change is accelerating. The ancient geological record provides some context. The Earth has undergone catastrophic changes before. The Permian-Triassic extinction, 252 million years ago, killed approximately 90% of all species. The Cretaceous-Paleogene extinction, 66 million years ago, killed the dinosaurs. The Lachance event, 41,000 years ago, weakened the magnetic field to a fraction of its current strength. Each event was accompanied by dramatic changes in multiple Earth systems simultaneously. Each event was, in some sense, a cascade of tipping points. We are not in a mass extinction event. The current rate of species loss, while alarming, is not comparable to the great extinctions of the geological past. But the rate of change in the physical systems that underpin the biosphere, the magnetic field, the ocean circulation, the atmospheric composition, the cryosphere, is faster than it has been at any time in the instrumental record, and is approaching rates that are associated with significant biological turnover in the geological record. The comparison is not meant to be alarmist. It is meant to provide perspective. The Earth system has modes of behavior that are beyond ordinary experience. It can undergo rapid, dramatic changes that persist for centuries to millennia. These changes are not caused by human activity alone. They are driven by the internal dynamics of the planet, by external forcing from the Sun and the galaxy, and by the interactions between all of these factors. Human activity, specifically the emission of greenhouse gases, is adding energy to a system that is already receiving anomalous energy from other sources. The effect is additive. More energy from human emissions, plus more energy from the Sun, plus more energy from the core, plus more energy from the cosmic environment, equals a system that is further from equilibrium than any single factor would produce. The human contribution is the one we can control, but it is not the only one, and the other contributions may be entering a phase of enhancement that amplifies the total forcing. This is the picture. It is not simple, it is not reassuring, but it is honest, and it is supported by data from every branch of Earth and space science, published in the most rigorous journals, confirmed by independent research groups, and consistent with the theoretical understanding of how complex systems behave when driven out of equilibrium. The Earth is changing, at its core, at its surface, at every layer in between. And the change has only just begun. The instruments are still recording. The data is still accumulating. The anomalies are still multiplying. And somewhere beneath your feet, in the iron heart of the world where no light has ever reached, a sphere the size of a small planet is turning in a direction it has not turned in decades. It does not know you are here. It does not care that your civilization depends on its behavior. It is simply following the physics. And the physics, right now, is producing something new. The Earth is not what it was. The measurements prove it. The animals sense it. The oceans reflect it. The ice records it. The volcanoes announce it. And the sky, filling with lights and sounds that have no precedent in the era of observation, displays it. You live on a planet in transition. The transition has begun. The evidence is everywhere. The only question remaining is not whether it is happening. That question is answered. The question is how far it will go, how fast it will unfold, and what the world will look like when the transition is complete. No one alive has seen the answer. The geological record has. And what it shows is that the Earth, when it decides to change, does not change gently. It changes completely. It rewrites the conditions of life on its surface. It resets the parameters. It starts again. Whether we are witnessing the beginning of such a reset is the defining scientific question of our era. The instruments that can answer it are running. The data they produce arrives daily. And every day, the data says the same thing. Something is happening. Something deep. Something connected. Something that links the iron core to the ocean surface, to the edge of the magnetosphere, to the boundary of the heliosphere. Something that has happened before, in ages when there were no instruments to record it and no scientists to interpret it. Only the rock and the ice and the fossils, preserving the evidence for a future species that would eventually find it and try to understand what had happened to the world before them. We are that species. We are finding the evidence. We are building the instruments. We are reading the data. And for the first time in the history of this planet, the species living through the change has the tools to see it coming. Whether we use those tools wisely, whether we act on what they tell us, whether we prepare for what the data predicts, that is not a question of physics. That is a question of choice. The planet does not choose, it simply changes. And the change, as measured by every instrument we possess, is already underway. Now you know. The rest is up to us.